Hello, we are team The Cases and the members are Nilesh and Ninad. Our project is Star Cluster Simulation.
This is Ninad and I'm going to talk about the dataset. The dataset has 19 timestamps and each timestamp has 64,000 stars. There are 8 columns in the dataset. This problem is very useful in the field of astrophysics. We consider only the analytics point of view. Let's see some of the visualization of the star cluster. This is a visualization for the star cluster over time. It changes from a tight cluster and it expands over time. Let's see some of the exploratory data analytics. As you can see, the correlogram shows that the columns are unrelated. Analysis of the magnitude of the distance over time shows that the number of outliers increases drastically over time. Similar analysis was done on velocity and this did not change drastically.
Hello, I am Nilesh. Here is a graph of the center of mass of the cluster with uh, respect to time. As you can see, it starts with zero and it varies with respect to time, which means that the stars are not stable. Uh, Here are plots of stars which have left the cluster and they are pretty random, which means that the timestamps were far apart. Uh, Here are some graphs which reinforce our assumptions of the star cluster movement. Histograms were done for the positions x, y, and z, and the histogram is used for the regression part.
First, a binary classifier that lists whether a star is present in the cluster or not was made using support vector regression. The training set was timestamp 1 to 18 and the test set was timestamp 19. All the outliers were labeled as 1 indicating out of cluster and 0 otherwise since data was unlabeled. The testing and training accuracy were around 95%. Time series analysis was done for those that left the class that were not present in the final timestamp. This indicates that they left the cluster. 30 points were of this type. The augmented Dickey-Fuller test shows that the data is not stationary. As you can see, the ACF and PCF for a particular star was plotted. The PACF had one spike and the rest were about zero. So a ARIMA model of 011 was made. The RMSE for such a model was 5.69. When the ARIMA model was made for stars that remain in the cluster, the RMSE for the test was 0.79. And here is a graph showing the predicted versus actual.
Uh, Two models were used, the linear regression and k nearest neighbors regression. Linear regression was used as the correlation was 0 and k nearest neighbors was used as closer planets were expected to behave similarly. Linear regression was used as the correlation was 0 and k nearest neighbors were used as stars which were close by were expected to behave similarly. Here are the results. As can be seen, linear regression has a smaller RMSE and it also ran faster as the uh, number of neighbors were 200, which is significant. Artificial neural network was done, but since the uh, error did not change for epochs 5 to 30, it indicates overfitting. And since the data set was large, more epochs were not done. Logistic regression was done on the same methodology as support vector regression, which was considering outliers, and since it's yes or no classification, it seemed suitable. Uh, Here is the comparison between ARIMA and multi-output regression. ARIMA was a time series analysis, while multi-output was based only on the present values. ARIMA could be done only for the magnitude, while each individual vector could be obtained from multi-output. ARIMA was quite slow when compared to multi-output, and the RMSE for ARIMA was 0.79 as compared to 1.41.
Comparing the SVR and the logistic regression model, accuracy for SVR was 95% and for logistic regression it was around 99%. SVR is slower than logistic regression, and SVR model predicts the probability, whereas logistic regression predicts the log of the probability.